Good day, everyone. This is the SCL presentation for Group 9. My name is Ilamaran Kannan and my matrix number is 223138 and these are my group members. So, for today's presentation, me and Mohammad Saifuddin bin Abdul Razak will be the presenters. So, let's begin with our problem, which is traffic flow modeling, where we need to find the ODE for traffic density, specifically using Lighthill-Witham-Richards LWR model. Basically, traffic flow modeling is a branch of applied mathematics and civil engineering that seeks to understand and predict movement of vehicles on a roadway. As urban populations grow and infrastructure becomes more complex, managing congestion has become a vital challenge for economic efficiency and environmental sustainability. ODEs was applied to stimulate how vehicle density changes over time and space using LWR model. So our model must be solved using Ranchkutta, Adam Bashford, and Adam Moulton for 2 iterations. So today we will be focusing on one of the methods, which is Ranchkutta Ford order method. Okay, our LWR model is dp over dt is equals to negative v dp over dx, where p is the vehicle count and v is the vehicle speed. Based on the dataset, P0 equals to 63, P1 equals to 50, P2 equals to 42, and P3 equals to 55. Then we need to find the data sampling interval H in hour by subtracting 15 with 0 and divided with 60 to get 0.25 hours. As we know, dp over dt equals to ftp, and ftp is equals to negative v times by kp. The value of V is 55.5 and the scaling factor K was assumed by 0.05 to get dp over dt equals to negative 2.775p. By using RK4 method, the step begins with T0 equals to 0 and P0 equals to 63. This T0 and P0 were applied to find K1 to get the answer negative 174.825000. So for K2, we will be using F bracket T0 plus 1 over 2 H P0 plus 1 over 2 K1H, whereby negative 2.775 times with 63 plus 1 over 2 times by negative 174.825000 times by 0.25 bracket to get the answer negative 114.182578. For K3, we will use the same formula as K2, where negative 2.775 times by 63 plus 1 over 2 times negative 114.182578 times by 0.25 to get the answer negative 135217918. So for K4, we will use a bit different formula where F bracket T0 plus H P0 plus K3H, whereby negative 2.775 bracket 63 plus negative 135.217918 times by 0.25 to get the answer negative 81.017569. So we will substitute the values of K1, K2, K3, and K4 into P1, where we will use the formula P0 plus H over 6, K1 plus 2K2 plus 2K3 plus 2K4 to get the answer 31.556518 for first iteration. So steps 2 will be continuous with second iteration, where we will choose T1 equals to 0.25 and P1 equals to 31.556518 from the previous answer. So for K1, we will use the same formula as previous iteration, where negative 2.775 times by 31.556518 to get the answer negative 87.569337. So for K2, we will use the same formula, whereby negative 2.775 bracket 31.556518 plus by 1 over 2 times by negative 87.569337 times by 0.25 to get the answer negative 57.163724. For the K3, we will use the same formula as K2, whereby negative 2.775 times by 31.556518 plus 1 over 2 times by negative 57.78 7193724 times by 0.25 to get the answer negative 67.730264. For K4, we will use the same formula as first iteration, which is a bit different from K2 and K3, where F T1 plus H P1 plus K3H, whereby negative 2.775 times with 31.556518 plus negative 67.6730264 times by 0.25 to get the answer negative 40.581469. So we will use K1, K2, K3, and K4 to substitute into P2 formula, whereby P2 is equals to P1 plus H over 6 bracket K1 plus 2K2 plus 2K3 plus K4 to get the answer 15.806569 for second iteration. That's all from me.
Next, I will walk you through the actual Python's implementation of the classical Ranjkuta RK4 methods as shown in our report and analyze the specific result we generated. First, we define two functions which is DEFFTP. This function represent our differential equation specifically for traffic model which is dp over dt equals negative 2.775 times p. Second, DEF exact solution T to verify the value for our model. Here we introduce P naught equals to CC3 and K equals to negative 2.775. Moving to the main Ranjkuta function, we initialize our simulation parameters. We set P equals to 63. This is our initial traffic count at the start of the observation. We start at the time t is equals to 0. We set the sample interval h equals to zero point 0.5. This is crucial because it means our algorithm will predict the traffic flow in 15 minutes interval 0.25 hours. The code then enters a loop using range 1, 3. Meaning we are asking the computer to calculate the two iterations specifically for this demonstration. For every single step, the code calculates four different slope estimated K1, K2, K3, and K4 to find the best path forward. For K1, we calculate FTP. This is the slope at the beginning of the interval. For K2, we take a half step forward. We use T plus 0.5h and adjust P using K1. This is us slope estimated at the midpoint. For K3, we take another look at midpoint, but this time we use the slope K2 to adjust our P. This refines our midpoint estimates. For K4, finally, we calculated the slope at the end of the interval T plus H, using K3 to get there. Once we have these four slopes, we updated P value. The formula used is a weighted average K1 plus 2K2 plus 2K3 plus 2 plus K4 divided by 6. This average slope is multiplied by our sample interval H and added to our current T. This gives us the predicted vehicle count for the next time step. Immediately after calculating the new P, we call the exact solution to find out what the value should mathematically be. We calculate the ABS error. This is simply the absolute difference between the exact value and our RK4 approximation. We calculate REL error. This divides the error by the exact value, giving us a fraction that tells us how large the error is relative to the size of the number we are calculating. Okay, now let's take a look at our final output. At time 0.5 hour, which is 15 minutes, the step 1 is the approximate P is equals to 31.556518. The exact P is equals to 31.481017. The absolute error is 0.075501. then the relative error is 0.002398. Similarly, for step 2, at time 0.50 hours, which is 30 minutes, we got this value. So, from the above coding and output, we can plot the graph for this method. However, if you look at the graph plotted from this value, we see an interesting divergence. The red line shows RK4 prediction, a smooth, perfect exponential decay. But the black dots represent the actual data provided. While RK4 predicts a drop roughly 50 cars at zero point 0.5 hours, the actual data shows 42 cars. Furthermore, at zero point 0.75 hours, the actual data spikes up at 255 while our model continues to drop. Conclusion is, this tells us that while our K4 code is perfect, actually solving the equation dp over dt equals negative 2.775p, the equation itself does not perfectly model the fluctuation of the real-world traffic data. The numerical analysis is sound, but the mathematical model requires adjustment to fit reality. That concludes the breakdown of our code and results findings.
Now, I will explain the advantages and limitations for Runge-Kutta fault order method. As we know, RK4 is a single-step method, which means it only needs the initial value to start the calculation. In our problem, we only need the initial value P0 equals to 63. This makes RK4 very useful for generating the first few data points needed for multi-step methods. One main advantage of RK4 is its high accuracy. It is a fourth order method, so it gives very precise results by evaluating the function at 4 points in each step. Because of this, RK4 is reliable and commonly used in numerical analysis. However, RK4 also has some limitations. For each step size h, the function must be evaluated 4 times. This makes it computationally expensive, especially when the model becomes large or has many variables. So, RK4 can be slower compared to multi-step methods. That's all from our group.